Wang from Rice, giving us a talk on math word problem generation with mathematical consistency and problem context constraints.
Hi everyone, thanks for the introduction, and it's great to be here to share our recent work on how to generate mathematical questions for educational purposes. This is a joint work with Professor Andrew Land at University of Massachusetts at Amherst and Professor Rich Baranook at Rice University and OpenStax. Let me begin by motivating the problem of generating math questions, or more generally generating questions for education purposes. And why do we need to do this automatically? For one thing, these questions in education are really helpful for learning. For example, in online courses, research has shown that frequent pop-up quizzes can significantly increase learning engagement, reduce dropouts, and lead to better or improved learning outcomes. Also, these questions can help knowledge retention, which is also very important to learning. For example, in this plot here, you can see that without these practice questions, you can forget what to learn very fast. However, with repeated practices, you can remember things much better than without these practice questions. So what's wrong with these questions in education? So one thing, currently, those questions are generated manually by educational experts, which is a very costly and time-consuming process. So what we would like to do is to reduce the time and cost for producing these practice questions. In addition, currently these questions are static, which means that all the students usually receive the same set of questions. So instead of this one-size-fits-all approach, what we really want is some kind of personalized learning in which the practice questions and hopefully other kinds of learning materials will adapt to the backgrounds, the interest, skill levels, and learning progress of each student. These kind of adaptive questions and other learning materials will make learning engaging and fun, and research has demonstrated the effectiveness of personalized learning approaches. So what we really want to achieve is some kind of a machine learning approach that can automatically and efficiently generate personalized and high quality questions. Specifically today, I will focus on a specific type of question in education called math word problems. Those are interesting and fun. I mean, those are questions that are super interesting and fun. And research has shown that these questions lead to improved students' learning engagement and improved mathematical proficiency. Each of these questions is usually associated with an equation, which is the math equation underlying the math word problem that the student is required to solve the problem. Each of the math word problem is also associated with a context, usually represented as a few keywords that put the equation into a little story or scenario that makes solving the math word problem fun and engaging. Okay, so how do we generate automatically these math word problems? We model the generation process in this pipeline that you see on the bottom of the slide. So we give the model an input that consists of an equation and the context keywords, and the output is the generated math word problems. Through this pipeline, we would like to control the generated math word problem by controlling or changing the input equation or the input context or both. So for example, if we change the input context from balloon to, for example, ice cream, we would like the generated math word problem to reflect this change. Similarly, if we change the input equation from 6 minus 2 to, for example, 10 plus 3, we will also want the generated math word problem to reflect this change. So this level of controllability will enable a human user to easily control what kind of math word problem that the user wants to generate. Something that's undesirable, for example, is when the generated math word problem does not match the input equation, for example, as you can see here, or the generated math word problem does not match the input context. So those are two scenarios we wanted to avoid. The question then becomes, how do we generate the math word problem that is mathematically valid and also relevant to the input context? So that's what our what our solution proposes. The first component in our method is the mathematical consistency constraint. The intuition is very easy. We use an equation generator to predict the underlying equation associated with the generated math word problem. And then we just enforce the predicted equation to be the same as the input equation. So in this way, we're imposing a constraint that the generated math word problem contains the equation that is the same as the input equation. So this is our way for enforcing the mathematical consistency. The second key component in our method is the context keyword selector. The motivation is that the context for each math word problem is usually unspecified or undefined, and it usually requires manual specification. What we desire is an end-to-end approach in this question generation pipeline in which we require minimum or hopefully no human supervision. So how do we do that? We design a context keyword selector which directly extract a set of informative keywords from the ground truth math word problem. We optimize this module with a KL divergence loss function, and we regularize this module to prevent the module from selecting too many keywords. During optimization, these three components are trained jointly, and the loss function comes from each of these modules. We have loss from predicting the math word problem, a loss from predicting the equation from the generated math problem, and a loss from the keyword selection module. Next, I will first show you some qualitative examples, some examples that demonstrate the effectiveness of our approach. Throughout these demonstrations, I would like to show you that one thing that I really wanted to demonstrate is how these different methods can adapt to the different context and equation combinations. For example, in this example, we use the same context keyword, and we pair this context keyword with different equations. And we wanted to see how the different methods adapt to the different pairs of input context and equations. In this example, we can see that our methods generate math word problems that are mathematically valid and also relevant to the input context, whereas the baseline methods generate math word problems that are irrelevant to the input context. In the second set of example, we perform the reverse. We use the same equation and we pair this equation with different context keywords. And we also wanted to see how the different methods adapt to the different input equation context pairs. Again, we see here that our method can generate math word problems that are mathematically valid and also relevant to the input context, whereas the baseline methods fail to adapt to the different the changing context in those two different cases. Next, I would like to show you some intuition of how our keyword context keyword selector is doing, and what kind of keywords the context keyword is selecting. In here, I show two examples, and you can see on the bottom of each of the tables, you can see the keywords that our keyword selector extracts. And you can see that those are the keywords that are informative to the underlying story or scenario for the respective math word problems, meaning that our keyword selector can extract informative keywords that are related to the context or scenario or the story of the underlying math word problem. We also compare our method quantitatively to a few baselines on 3 different datasets. Here we evaluate on 2 sets of metrics. The first group of metrics evaluates the language quality of the generated math word problems, and the second metric evaluates the equation consistency of the generated math word problems. For all these metrics, the higher number, the better. And we can see that our method for in each of the dataset and across all evaluation metrics, our method performs better, on par or better than the baseline methods in most of the cases. And last but not least, here are some additional qualitative examples that shows the high quality of the math word problems that our method is capable of generating. Okay, so now we have a method that can generate math word problems for math learning in the education scenario. But beyond that, we have many other types of questions for a wide range of curriculums. Right? Our final goal is to be able to design systems to enable the generation for many different kinds of questions for diverse curriculums. So here are some of the next steps that we are planning of doing to expand this line of work. So first of all, we wanted to generate questions that involves multiple modalities. In addition to math language and natural language, we also wanted to incorporate images and tables and maybe some other types of information into the question generation process. We would also wanted to enable more complex controls. So for example, in this case, during the generation process, we have control over the context and mathematical equation. Ideally, we would also want to control the linguistic complexity in the generated question, and also the appropriate difficulty of the questions to adapt the question difficulty for different skill levels of individual students. We would also want to design a question generator that is verifiable and safe, such that they can be responsibly and reliably deployed in practice. And finally, we also wanted to investigate the impact of the generated questions on actual student learning. So we can compare the effectiveness of the generated questions with real human-generated questions and see how those generated questions can improve human learning. There are a lot of more technical details, resource analysis in our paper, and the link is in the QR code, which you can refer to and find more of what you are looking for in our paper. Thank you for your attention, and I'm looking forward to any questions that you have.
Thank you, Jack. We have one question. Which are the different types of equations that this method can take as an input?
Yes, this is a great question. The question asks about the kind of input equations that the model is capable of generating. So currently, the model, the equation we're focusing on is very simple. We focus on equations that contain a single variable and single equation. So currently, for example, systems of equations involving multiple variables. This is part of ongoing work, because the thing is generating those generating math word problems from those simple equations is already a very challenging task, and we are taking the very first steps towards generating mathematically consistent word problems from those equations. But yes, we are focusing on simple equations right now.
Okay. Thank you. There's another question. For your broader goals, do you believe generating the question is easier or harder than answering it?
This is another great question. I think, for me personally, hopefully you have a different perspective on this. For me personally, I think generating the question or asking the question in general is more difficult than answering it. And this is one of the challenges for generating math word problems, because to make the generated question be consistent with the input equation and input context is very challenging, because there are more goals than merely to answer the math word problem. There are a lot of research on how to answer the math word problem, but the reverse is much less than trying to answer the math word problem. But in general, I think to generate the question is more challenging than answering. That's why we're interested in this problem.
Mm-hmm. Sounds good. Thank you for for the great presentation.
Thank you.
All right.